One of the biggest factors that can affect the performance of queries is indexes. So what are they and how do they work? You create an index on a table, and when you create it, you specify one or many columns from that table that are part of the index. And what that does is create a search-optimized copy of the data from those columns. It's a fast lookup data structure that lives on disk. When you create an index, it doesn't modify the underlying table at all. It just creates a new data structure that points to records in the original table. And that data structure is optimized for fast lookups versus just scanning the entire table. So after you create an index on a table and issue a query on that table, if the query utilizes the index, then it will first go to the index to quickly search for the records you're after, and then follow the pointer to the actual table data which is on disk to retrieve it. Without an index, the only thing that's possible to do is a sequential scan of the entire table, looking for the records that you're after in your query. In many ways, you can think of a database index like the index in the back of a book. If you want to find references to a particular word in a book, you can go to the index at the back of the book. It's sorted alphabetically, so you can quickly find the word you're looking for, and then the page numbers of the book to jump to. Without an index in the back of a book, the best you can do is to read every single page of the book looking for the word you're after. Indexes are basically the number one tool in your toolbox when it comes to query performance optimization, so it pays to become very familiar with them. In the absence of an index, as I mentioned, reading the data sequentially from disk and checking each record is really the only way to go. But creating an index comes with a cost. It's a whole new data structure that first needs to be built if your table already has data in it, and it also needs to be maintained. So as you perform inserts, updates, and deletes on the original table, entries have to be updated in any related indexes. Having said that though, indexes are a lot less expensive to maintain than you might think, so if in doubt, you can err on the side of adding in an index versus not doing it. In Postgres, you can create indexes on both tables and materialized views. And there are actually quite a few different kinds of indexes that are available in Postgres, suitable for different types of queries and different data types. But by default, if you don't specify the type of index that you want, you'll get what's called a B tree, which stands for Balanced Search Tree. It's a good general-purpose index that's common to many relational databases, and it works well for a variety of different use cases. It's also the index that automatically gets created behind the scenes for you when you set a primary key for a table or create a unique constraint. Each of those will have a backing index that's created for you. Let's look at an example of taking a query that just performs a sequential scan, creating an index, and then seeing the query leverage that index to obtain a performance gain. For this example, I already have some SQL statements queued up and ready to go. I'll be walking through them and explaining each one as I go. I'm going to start by creating a new schema called test, and then I'm going to create a table within that schema called messages. In this table, there are 3 columns: ID, account ID, and message. The idea is that this table would be storing messages that, say, a user might send to somebody else. Each message has an ID, the account ID represents the user, and the message is the actual text. Let's create that table now. The next statement, the insert statement, inserts a bunch of test data into it. I'm using the generate series function so that I can generate 1 million records. So the ID column will count from 1 to 1 million. The account ID is just going to be a random number between 0 and 100,000. And the message is going to be some substring of "Hello, are you there?" always of length 5. So it's a very large table just containing some random data that's good for demonstration purposes. Let's run that. Depending on how fast your computer is, it might take a while. For me, it was just a few seconds, but it is generating 1 million records, so there's quite a lot of data in this table. The next SQL statement is something new and something you haven't seen before. I ran a command called vacuum analyze on the messages table. After initializing a new table or loading it with a really big amount of data, you always want to run this command against the table to ensure the statistics are up to date. That's what this command does. You'll recall that earlier I talked about how the query plan is generated based on statistics that are available for the table. And if the statistics aren't up to date and accurate, you can get suboptimal query plans when you write queries against the table. Running vacuum analyze after a big data load into a table ensures that the statistics are fresh and up to date. Okay, so let's have a look at the contents of this table. I'll just pull out 100 records. So you can see that ID is sequentially increasing. Account ID is a random number between 0 and 100,000. And the message is some substring of "Hello, are you there?" Presently, this table has no indexes on it. So if we look at writing a query where we select the ID and messages, where the ID is 33, the best we're going to get is a sequential scan. Let's run explain analyze on this query just to verify that looking at the query plan. And I'll introduce you to something new and interesting as well. Let's pull this up and look at the query plan. Ultimately, at its heart, this query plan is really just a sequential scan. However, it's what's called a parallel sequential scan. A parallelized query is one whose execution is distributed by the planner across multiple different processes. Essentially, Postgres split up this job, this query to be run, across multiple different processor cores on your hardware, enabling it to speed up the execution of the query. But ultimately, this is still just a sequential scan. Every record from the messages table was read from disk, with the ID being checked against the value 33. Even though it got parallelized, it's still a very inefficient way to go about searching it, and our execution time was around 44 milliseconds. Let's now go ahead and create an index on the messages table on the ID column. We can do that with this create index statement. We're not specifying the type of index to create, so we're going to get a B-tree index. Let's now go ahead, after creating this index, and run this select statement again, and look at the query plan that we get. Our execution time has dropped from 43 milliseconds to 0.058 milliseconds. That's an enormous performance increase. And we're no longer doing a sequential scan. What's happening now is what's called an index scan on the messages table. What an index scan does is first go to the index, the fast lookup data structure that we created on the ID column. Because this is a fast lookup data structure, it's able to find the record where the ID is 33 almost instantly. So it finds the record in the index that has an ID of 33, and then it goes to disk and reads out the actual data from the table itself based on the pointer. So this query now was able to avoid reading the entire messages table. It didn't have to go to disk and pull out every single record. Leveraging the index, it was able to quickly identify which row it wanted and exactly where on disk that was. It was able to follow that pointer and pull out only that page from disk. We can make things even faster though, and I'll show you how. To do that, what I'm going to do is drop the index first that was just created, and I'll create a new index. When I created the index, I didn't specify a name for it, so it got given a default name of messages_ID_IDX. If you want to verify that, you can actually go into the database navigator. Let's see our new test schema. We can go to tables, messages, indexes, and there's that index that we created earlier, messages_ID_index. It got given a default name. Let's drop that index. And now let's create a new index. Let's create what's called a composite index, an index over more than one column. So in my index now, I want to index both the ID and the message columns. I'll create that now. And now let's run this query again, and let's look at the query plan. In this case, I got what's called an index-only scan. Typically, index-only scans are even faster than just index scans. And the reason why this became an index-only scan is because the data that we request in this query, the ID and the message, can be obtained by looking at the index alone. There's no need to follow a pointer to retrieve the actual table data from disk. Everything that we want, we can get out of the index alone, the index only. Missing indexes are the #1 cause of query performance issues. So in future, if you've got a poorly performing query, look for signs of sequential scans on large tables and investigate what indexes you can add. As I mentioned before, it is possible to over-index a table, but you can, generally speaking, err on the side of adding too many indexes and then walk that back later if that's causing other performance issues.